Zener diode voltage regulator, which is the last topic of the system which converts AC signal into DC signal. Okay. If you consider back the basic block diagram of the system which converts AC signal into DC signal. See here. First, we have a step down transformer which converts 230 volts to around 10 to 20 volts, like that. It's a step down transformer whose output voltage is a pure AC signal. It's a bipolar signal, AC signal, and which is acting as input to the rectifier. The rectifier may be a half wave rectifier or a full wave rectifier, which converts the bipolar signal into unipolar signal. Of course, here this is the output of full wave rectifier, and this signal can be represented as a combination of DC and AC according to Fourier series and all we know. And this unwanted AC is known as ripple signal. Here our concern is to produce as much DC as possible, right? That's why we should pass it through a filter, and the filter here is more precisely, I can say it is a low pass filter which eliminates all high frequency components. Okay, and it or I can say it reduces the AC level and improves the DC level, and the output of the filter is known as variable DC. Here the ripple component is very less. Okay, and here in the previous lectures we have seen if the load resistor is connected at the output of the filter, whose output voltage is something like this, capacitor charging, discharging, etc. All those things we have seen, and whose output depends upon the load resistor. If RL is small, then ripple component is more and DC component is less. If RL is large, ripple component will be less and DC component will be more. Means the expected DC output of the filter depends upon the load resistor. Okay, that's the issue we are facing with filters. So what we do, we are going with the next stage to see that our output is not dependent on the load resistor. We are using a stage known as voltage regulator. To be frank, what this voltage regulator does means it maintains a constant output voltage independent of variations in its input. Variable DC is the output of filter, low pass filter. That variable DC is converted into a proper DC. Okay, so if I take this one, voltage regulator diagram, whose input is a variable DC, output of the filter, and output load resistor may vary. So here what it does means a voltage regulator maintains constant output voltage independent of variations in input voltage and load resistor. How is it possible? We have to see. And how does the circuit appear? Actually, such action is possible with Zener diode. If you look at the characteristics of the Zener diode, right here I have shown. So Zener diode is mainly used in the reverse bias condition, right, instead of forward bias. In forward bias, it behaves like ordinary PN junction diode. So the forward bias characteristics of Zener diode are like this, and the reverse bias characteristics are like this. What is the meaning of these characteristics? We have to see. See, here I am not considering the construction operation of Zener diode. I am taking the conclusions of characteristics which we study in devices, electronic devices and circuits. Okay, so if you take the case like first case 1, the Zener diode forward bias condition means V input R, and whenever we forward bias in the sense, see, anode is connected to positive terminal and the cathode is connected to negative terminal of the device. So when it is forward biased, the current flows from anode to cathode, whenever positive to negative terminal of the supply, and voltage across the diode is denoted by V. Okay, so I is the current flowing. I is in clockwise direction and V is from anode to cathode. So in forward bias, Zener diode behaves like ordinary PN junction diode. Very simple statement. And the characteristics are like this. Ordinary PN junction diode. Okay, V gamma. So voltage across the diode is greater than V gamma. V is greater than V gamma. We can take this way. And case 2. Reverse bias. Reverse bias in the sense, of course, the input is less than its breakdown voltage. Then the Zener diode behaves like ordinary PN junction diode under reverse bias condition. So in reverse bias, with V input less than Vz, Zener diode simply behaves like open circuit, or acts as open circuit, I can say. Zener diode acts as open circuit. Case 3. Reverse bias with input greater than its breakdown voltage. Then how does it behave? If you look at its characteristics in reverse bias, okay, these are the reverse bias characteristics. Once the input is greater than breakdown voltage, then it starts conducting in the reverse direction. Suddenly the current through the Zener diode shoots up, but it maintains constant voltage. It behaves like a voltage source, almost like a voltage source, maintaining constant voltage with a variable current. Okay, so the Zener diode in reverse bias with V input greater than Vz, Zener diode starts conducting in the reverse direction, or Zener diode undergoes Zener breakdown and starts conducting in the reverse direction. Means the current will be flowing anyway positive to negative terminal of the supply in the reverse direction. I can call this current as I said, and it maintains a voltage Vz from cathode to anode. So direction of the current only. Okay, in the previous case, the current is clockwise and the voltage polarity is from anode to cathode. Whereas here the current is in anti-clockwise and voltage polarities are from cathode to anode. If that is the case, IZ and VZ are negative. If I take I and V as positive, current is positive, voltage is positive, plus plus, it is in the first quadrant. Here IZ and VZ both are negative and hence the characteristics are shown in the third quadrant. Current is negative, reverse current and reverse voltage. Current and voltage are negative. In forward current, forward bias, right, current and voltage both are positive, plus plus. So here in the first quadrant, we can see that. Once it undergoes breakdown, it maintains a constant voltage Vz from cathode to anode and a current, variable current. Current is suddenly shooting up and current flows from cathode to anode as well. Okay. So it maintains, what I can say right further is, it maintains, Zener diode maintains a constant voltage from cathode to anode and variable current from cathode to anode. Okay. Zener diode maintains constant voltage Vz from cathode to anode and variable current. Iz. Okay, this is what we can understand. Okay, now if you take this circuit, this particular circuit, if I take the loop equation, what we can write is minus V in, anything you can write, or plus V in also, doesn't matter, plus Vz plus Iz into R is equal to 0. Okay, and the same circuit I'm rewriting like this. I'm changing the polarities of the supply and change the direction of the Zener diode as well. V input which is greater than Vz R and it is Vz. The current always flows from positive to negative terminal of the supply and this current is Iz. And Vz polarities are from cathode to anode. Now see this. Okay, you may be thinking like it's a positive supply. But the thing is, I changed the direction of the Zener diode. So cathode is connected to the positive terminal and anode is connected to the negative terminal of the supply. And if I take the loop equation here, minus V input plus Iz into R plus Vz is equal to 0. This equation and previous equation, if you see, both are one and the same. Okay, just I am changing the polarities of the supply, accordingly changing the direction of the Zener diode. Now here what happens is, it is maintaining a constant output voltage with variable input greater than Vz. I can change the input, doesn't matter, and but it maintains constant output voltage Vz across it, which is the property of it. And of course the current through the Zener diode is varying. Okay, just what you can understand from the characteristics means the current through the Zener diode is varying. Okay, so it means, see, I can prepare one table. I'm just taking a case where the resistor value is around 1 kilo ohm and Vz is around 5 volts. Just as an example, for example, R V input, R is equal to 1k and Vz is equal to 5 volts and input is greater than 5 volt and there is a current flow. this is Vz is equal to 5 volt output voltage. Just I'm preparing one table. V input, Vz and Iz. What we can write for Iz? Iz is equal to V in minus Vz by R. This is V in, this is Vz by R. That gives us Iz. For example, input is around 1 volt. Then it doesn't undergo breakdown. Current will be, it acts as open circuit, means current is 0 and V is equal to Vz. Current through the V is the voltage across the Zener diode. I can write, and it is current through the Zener diode. So voltage is equal to 1 volt. Or I is equal to V in minus V by R. Anything you can write. Next, suppose it is 3 volts. Again, there is no current, and I can write here further the entire voltage can be seen across the Zener diode. Almost it behaves like open circuit. Once the input is greater than its breakdown voltage, something like some 6 volts, then the Zener diode undergoes breakdown and it is equal to 5 volts. And what about the current? I is equal to 6 minus 5 by 1K, it is 1 milliampere. I can say this current is Iz, it is 1 milliampere. Current will be flowing. Further, I am increasing the supply, maybe some 8 volts. Then once it undergoes breakdown, even though we vary the input, right, it maintains constant voltage across it. And it can't maintain constant current. It can vary the constant voltage with variable current. So what is Iz here? It is 8 minus 5 by 1K, it is 3 milliampere. Like that. Suppose it is 18 volts, still it maintains constant voltage. So the current will be 13 milliampere, like this. So even though you are varying the input voltage, it maintains constant voltage across it with variable current. Okay, so the first case I am able to achieve. It will maintain a constant output voltage independent of variations in input. Of course, there is a limitation. You can't get 5 volts from 2 volts, right? At least input should be greater than the breakdown voltage. Then you can see a constant output voltage of Vz. That is the idea here. We have to see how the output voltage is independent of the load resistor. That is the next part. First, we are at the basic level, at the very beginning stage. So that is possible. Just if you observe the Zener diode characteristics, it is ready to maintain constant voltage with variable current values. Okay, it is also fine. But here there is one obligation. If you calculate the power dissipation in Zener diode, what happens is, which is given by Pz is equal to Vz into I. If the input increases, if the input is increasing, then what about Iz? Vz is constant, but Iz keeps on increasing, which implies Pz keeps on increasing. Vz may be constant, voltage across the diode is constant, but the current through the Zener diode is increasing, which causes the power dissipation in Zener diode to rise. As the power dissipation keeps on increasing, then there is a scope that the power dissipation in Zener diode may exceed the rated power. Every device has its power ratings. Diode, BJT, FET, op-amp, Zener diode, anything, right? Light emitting diode, photodiode, any device you take, they have their own limitations. Okay, so more power is dissipated in the Zener diode, then right, that should not exceed the power rating of the device. If it exceeds, the Zener diode will immediately burn. So there is a limitation on your input. You cannot apply any input less than breakdown voltage. First point. Next, if you are applying an input which is greater than its breakdown voltage, fine, but it has its own upper limit, such that Pz should be power dissipation in Zener diode PZ should be less than or equal to PZ rated, or a rated power, which is known as rated power or power rating of the Zener diode, or rated power or minimum power rating. The terminology you see, minimum power rating. Okay, so PZ means the power dissipation in Zener diode. Already here I wrote it, power dissipation in Zener diode, or you can even write maximum power dissipation, that also can be written. Maximum power dissipation in Zener diode should not exceed its rated power or minimum power rating of the Zener diode. See, it is the terminology, right? It is a specification. Look at the terminology. It is a specification, and here it is variable. Right? It depends upon the input. Depending upon the input, the power dissipation in Zener diode. And the maximum allowable value should not exceed the power rating of the Zener diode. Means there is an upper limit for the current through the Zener diode. Okay, so which means I can say PZ maximum, or PZ is equal to PZ maximum is equal to VZ into IZM. There is an upper limit for this, which is should be less than or equal to PZ rated, power rating of the Zener diode, which means IZM is less than or equal to PZ rated by VZ. Current through the Zener diode should not exceed this value, which is shown here. IZM, it is one specification. IZ maximum, it has its own limitation. If you apply the input such that the current through the Zener diode exceeds the rated maximum allowable current, then the power dissipation in Zener diode exceeds its rated power and Zener diode simply burns. So we should be careful. There is an upper limit for input. Next point, if you decrease the input voltage, right, instead of 18, I may set the input at some 12 volts. Then what happens? Still it maintains 5 volts. There is an upper limit, right? You can increase the input to a maximum value, V max, I can write. Okay, and up to that it maintains 5 volts, and I can say it is IZM. It is IZM is a specification of Zener diode. One specification of Zener diode. Okay. Next, further I am decreasing the input. If we decrease the input voltage, right, suppose it is like some 12 volts, then still it is 5, it is 7 milliampere. Right, if suppose it is some 6.5 volt, then still it maintains 5.5, so 1.5 milliampere, just as an example I am writing. Okay, further I am reducing, suppose it is 5.5 volt, still it may be 5 volts and it is 0.5 milliampere. So which means as we keep on decrease V input, then current through the Zener diode also decreases. Okay, fine. Again, here we have one more specification. As you keep on reducing the supply voltage, the current through the Zener diode decreases and it approaches a value that is IZ minimum, known as knee current. If current through the Zener diode falls below this knee current, immediately Zener diode comes out of breakdown. If current through the Zener diode as we keep on reducing the input, current through the Zener diode keeps on decreasing. Decreases, and for a particular value of input, or and if V input falls below certain value, Iz falls below its minimum value. Iz falls below Iz minimum, or it is also known as the knee current, I knee, then Zener diode comes out of breakdown. And no more maintains constant voltage, and it no more maintains constant voltage is said across it. This is the meaning of this characteristic. Iz falls below I knee. Why the name knee current? If you observe this, it looks like the shape of a knee. Once you see, bend your necks. If you sit, then we can see the knee. There is no big rocket logic behind it. Sorry, right, rocket science behind it. It's a simple thing. Just if you bend your knee, it looks like the shape of a, right. So there is a bend. You can see, right. It looks like the characteristic is looking like the knee shape. Okay, that's why the name knee current. Okay, done. So as long as the current through the Zener diode is in between Iz minimum and Iz maximum, it maintains constant voltage, we said. So current is variable, but voltage is constant. That is the property of a voltage source. Okay, a voltage source maintains constant voltage across it with variable current. This property I am using in voltage regulator. Okay, there is a minimum limit for V input, no doubt about it, such that current through the Zener diode should not fall below knee current, and there is an upper limit for V input such that current through the Zener diode should not exceed Izm. As long as the current through the Zener diode is within this range, then it maintains constant output voltage Vz across it. Okay, so this zone we can use. Once it is able to maintain that, once you are able to maintain the current through the generator between Iz minimum and Iz maximum, you can vary the input with minimum and V input maximum. Then we can see constant output voltage across it. Means voltage regulator circuit. How can we show this voltage regulator circuit? If you see so, this particular portion. Is it not so variable input? This resistor and Zener diode combination behaves like a voltage regulator. You can vary the input here, but you can see constant voltage. By varying input, IZ may change, but output does not change. Okay, that's what you can see. So a voltage regulator circuit, how does it appear? A voltage regulator circuit. I'm just drawing this. V input, some resistor and Zener diode. Input should be greater than breakdown voltage. This is voltage regulator. And here we can connect the load resistor, then RL. Without load resistor, what we can see here is, I said it is IZ and VZ like this. Okay. Now, once you connect the load resistor, I can't use the same notation. Some load resistor is connected, V input R. Then when you are connecting a load resistor, there is a current IL through it. And current through the Zener diode is IZ. Current flowing from the input, I cannot call this current as IZ, I can call it as I. I is equal to IZ plus IL. And voltage across RL, it is VZ. This is how the circuit appears. Okay. Without load, this is what we can see, voltage regulator, and with load, this is how the circuit is appearing. Here, the input is variable, right? We can see if RL varies, also how it maintains constant voltage, we have to see that. Okay. As long as current through the Zener diode is between IZ minimum and IZ maximum, we can see constant voltage across RL. And what are the various equations in this? We can see means I can write I is equal to V in minus Vz by R. It is V in, it is Vz by R, that gives us I. And what about IL? It is our V output is equal to Vz see this. Okay, these are simple things only. If I take this loop equation, V input is equal to I into R plus Vz. V input is equal to I into R plus Vz, or I is equal to V in minus Vz by R. Okay. Next point. V output is equal to Vz is equal to IL into RL. Or I can write IL is equal to Vz by RL. Next, the node equation, if I take I is equal to IZ plus IL. That's it. Okay, we can use these equations. And what about the power dissipation in Zener diode? Or what is the Q point, operating point? At what voltage and current the device is operating? I can say the Q point of Zener diode. It is Vz comma IZ. And power dissipation in Zener diode. Vz is equal to Vz into IZ. That's it. These are the points to be observed. As far as a regulator is concerned. Then we will see later on, right, how to find the range of input. What is the minimum value of input so that the Zener diode maintains constant voltage VZ across it, or what is the maximum value of input? We need to see that. And how the output is maintained constant independent of RL. Suppose RL is 0, definitely output will be 0. There is a minimum limit for RL. Okay, and there is an upper limit for RL as well. As you keep on increasing RL, the output, right, the things will change. How? We have to analyze all those things. Nothing to worry at this stage. Okay, and one more point I would like to mention here. If in a problem, if IZ minimum is not given, then assume IZ minimum is equal to 0. If IZ minimum or IK knee current is not mentioned, assume that knee current is equal to 0. Please do remember. And we have not yet discussed anything about RL. We will see that. And if RL is not given, then assume RL maximum is equal to infinite. RL minimum, you can't take it as 0, but RL maximum can be assumed as infinite. Right? If RL is not given, is not mentioned, then assume RL maximum, friends. It is not RL minimum. RL maximum is infinity. Right? These are some points to be observed. There are a lot of cases we need to analyze. Range of input, range of RL, and range of this resistor R. R is known as series resistance. R is known as series resistor. Please do observe this point. Now, let us have a look at some basic questions on this regulator. See, if you look at the characteristics, these are just nothing but the characteristics of a voltage source, right? If you take a voltage source, I have not shown here, right? Voltage source, if you consider what does it do? It maintains constant voltage with variable current. Okay, or if I take the voltage source characteristics, it maintains depending upon the load we are connecting. RL may vary, but right, depending upon the value of RL, if I take VI characteristics, it's voltage with respect to time. Here I am writing voltage with respect to current. It maintains constant voltage, ideal characteristics I am writing, right? It is maintaining constant voltage V or Vx, let it be, right? I can write Vx is the value with different current values. The current depends upon, current is equal to Vx by RL. Depending upon RL, the current value will keep on changing. Ideal characteristics of voltage source. Okay. So, that's what. We are designing a voltage source, only DC power supply voltage source we are designing. Regulator means what is output, right? Here, it is something like this. This characteristic and this characteristic are matching. Okay, so such thing is possible with we need to discuss that how it is independent of RL, except that, right, the Zener diode is exhibiting a characteristic of a voltage source with some limitations on its current. You cannot take IZ for any range. There is a minimum limit and there is a maximum limit. Then one more point. See, here I showed with a vertical, perfect vertical line, the characteristics. I showed like a perfect vertical line. Okay. So what is the slope of this vertical line? That is infinite. I can say the slope, here I am speaking, or here I am writing, slope is equal to delta Vz by delta Iz. But it is infinity. Okay, because it looks like a vertical line. Or it is, I can write 1 by Rz, or Rz is equal to the Zener diode's internal resistance. It is 0. Means it is behaving like ideal voltage source. Means the equivalent circuit of Zener diode is, if I take this, its equivalent is like this one, Vz, and current can be any value. Okay. Cathode to anode, it is maintaining constant voltage. And it is like an ideal voltage source. Ideal voltage source is internal resistance is 0. Okay. Whereas, of course, there are some limitations. Whereas the second case I am taking here is this one. There is a small change. There is a small slope. Okay, you see this. There is some variation in Vz and there is some variation in Iz. Let me take 2 points. This is one point and this is another point. These 2 points I am taking. So which means this is one point and this is with respect to these points we can, or this one and this one. This is delta Vz I can write, and I can say this current is delta Iz. Okay. Here this is one Q point. Q1 is equal to V1 and IZ1 or I1, anything we can write. And this is another point. Actually, this is the another point. This is another Q point, I can say. It is V2 and the corresponding current is I2. Okay. So, then there is a slope. What is the slope of this line? We can write slope is equal to change in y coordinate, that is delta Iz by delta Vz. I can call it as 1 by Rz, slope of this line. Okay. So it's not a perfect vertical line. There is some slope. Instead of infinite, it is having some value. Then with the slope, let us take this straight line equation. So further I am extending this line. This one. Let me take this voltage, extending this line. Right. If I extend this line, let me call this as Vz. Actually, it is a V1 and V2. If they are very close to Vz, no doubt about it, but slightly greater than Vz. Suppose Vz is equal to 5, then Vz1 may be 5.1 and Vz2 may be 5.15 volt, like that, just for our understanding seconds. Slightly greater than Vz. Right, V1 and V2 are slightly greater than Vz. Okay, then what is the straight line equation? Let us take the straight line equation. If I take this one, what are the coordinates with respect to this particular point? The y coordinate is, okay, Vz, sorry, x coordinate is Vz and y coordinate is current is 0. Okay, so straight line equation, if I take it, y minus y1 is equal to m into x minus x1. What we are taking along y-axis, it is current I minus y1 x1. I am just taking this as my coordinates. That is, okay, I can even write it like minus Vz comma 0. Okay. Then the y coordinate is equal to y1. It is 0 is equal to, what is the slope? 1 by Rz into x means it is V minus Vz. I am just taking the magnitude value. Okay. The thing is, uh, why I'm writing only VZ means, see, we have further changed the equations this way. Okay. Nothing else. I want to find the slow straight line equation, nothing else behind it, so that I can even write it like I is equal to V minus Vz by Rz, or V is equal to, or I can say Iz, no, Vz and Iz are the coordinates, no, and Iz is the current through the Zener diode, or Iz. Okay, then V is equal to Iz into Rz plus Vz. We can write like this. Actually, this kind of analysis we did in diode models as well. Okay, if the diode characteristics are taken like this, then it is V gamma and the slope is equal to 1 by Rf. Remember? Then there also we wrote the equivalent circuit. If I take the diode, then what we are writing here, there is a resistor in series with V gamma and it is Rf, where Rf is equal to, right, 1, the reciprocal, our slope is equal to 1 by Rf. We remember this point. Okay, this equation and this equation, just similar only. So what is the equivalent circuit of our Zener diode? To be frank, what I can do is, if you think like, anyway, not required, I'm just writing it, I should take here negative sign and here also plus, then the things will be coming, right? Instead of doing all such things, just I'm directly writing the equations. So V is equal to Iz into Rz plus Vz, means wherever we have this Zener diode, instead of Vz I'm writing V and this current is Iz, then its equivalent circuit is like Vz, Rz, Iz and V. Okay, like this we can write. If it is a perfect vertical line, then Rz will be 0 and V is equal to Vz, and that's what our previous case. This is much practical version, right? This case is much practical version. Regulator with Rz. Okay, but we study both the cases, right? Ideal Zener diode, if they mention, then Rz is 0. Okay, if they give the value of Rz, or if they show the characteristics like this and mention delta Vz, delta Iz, etc., then we have to take Rz into consideration. Okay, these are the two cases we have as far as the characteristics of the Zener diode are concerned. Okay, actually we are plotting these characteristics in the third quadrant, means strictly speaking I should write here it is minus and here it is plus. In that context also what we get is the same result. V also becomes negative, right? V is negative, then you can see the results. Okay, you will get the same equation. Is it not so? V and I are taken in the third quadrant. In that context, I should write here minus V and here it is minus I, where I is of course equal to Iz. Okay. Instead of all such things, I changed it this way. Sorry. I hope students can understand this. Okay. So now let us have a look at some problems on what we have discussed so far. Later I will discuss various cases like what is the range of input, what is the range of load resistor, what is the range of R, R in the sense this one series resistance, how the output is maintained constant even though we are changing input value or R value or RL value. All these cases we need to discuss. They are very simple only, right? See, you take any Zener diode circuit, you won't get equations more than this. These are the equations, nothing else. Okay. But still students do mistakes on these things. Okay, let it be. So this is the basic regulator circuit, and I'm following the notation like this is I, this current is IZ, VZ has polarities from cathode to anode, current through RL, it is IL input. We know the equations and all. Then see the first question. Ideal characteristics of a stabilizer. What are its characteristics? It maintains constant output voltage with zero internal resistance. So constant output voltage with low internal resistance, option A is correct. Remaining options, no need to see. Constant output current with low internal resistance, not possible. Constant output voltage with high internal, meaningless. Constant internal resistance with variable voltage, meaningless. A Zener diode, when used in voltage stabilization circuits, is biased in reverse bias with above breakdown voltage. Option B is correct. Operates in reverse bias. Now see this one question. The Q point of the Zener diode shown in figure. What it might be? It's a Q point. Means IZ and VZ they are asking. IZ, IL, current I. So we can first write I is equal to V in minus VZ by R. It is 20 minus 4 by 11 kilo ohm. Okay. So it is a 16 by 11, 1.45 milliamperes. We can see. Okay, 4-3. 16 by 11, no? 11 ones, 15. Yes, 1.45. Approximately, I'm writing it. Then, what about IL? IL is equal to V output by RL. R output is VZ, VZ by RL. It is 4 by 3.6 into 10 power minus 3. Sorry, kilo, no? So, 4 ones, 10 by 9. It is 1.11 milliampere. So, IZ is equal to I minus IL. It is equal to 0.34 milliampere. So, 0.34 milliampere with 4 volts. Option A is correct. It's a simple calculation. At Q point. Anyway, they asked current and voltage. What is there in it? They may be taking current along x-axis and voltage along y-axis. Let it be. Accordingly, we can see. IZ and VZ. In the voltage regulator circuit shown in figure, find the output voltage, voltage across series resistance and current through the Zener diode. Okay. So simple thing. What is output voltage? Simply it is 50 volts. And voltage across the series resistance, this current I is equal to V in minus VZ by R. So 20 minus 50, 70 by 5, 14 milliampere. Voltage across, no? So that is 70 volts. 120 minus 50. Current through the Zener diode. Okay. This current they are asking. Anyway, we got I. IL is equal to VZ by RL. It is 5 milliampere. And IZ is equal to I minus IL. 14 minus 5, 9 milliampere. That's it. In the voltage regulator circuit shown in figure, find the maximum and minimum values of current through the Zener diode. Okay. Here we know, right? I can write I here and this is IZ and IL. If input is minimum, then current through the Zener diode is minimum. If input is maximum, current through the Zener diode is maximum. Simple. So the first case I can take like this. $80 5K, 50 volts 10K, IL, IZ and I. So what about IL? It is VZ by RL. It is 50 by 10K 5 milliampere. It is same for all the cases because RL is fixed. No, RL is not changing here. Okay. What about I? As input is minimum, I can say I is also minimum. I is proportional to input. Okay. I is equal to 8V input minus VZ by RL. So 80 minus 5. It is 70. Sorry, 30 by 5. It is 6 milliampere. Then IZ is equal to I minus IL. It is 1 milliampere. Simple. And the second case, if input is 120, IL is not changing. What is the value of IL? As usual, it is 5 milliampere. And I is equal to 120 minus 50 by 5K. So 7 by 70 by 5, 14 milliampere. Then IZ is equal to I minus IL. 14 minus 5, it is equal to 9 milliampere. Okay. The range of IZ is 1 milliampere to 9 milliampere. Right. If 80, the corresponding IZ is equal to 1 milliampere, and it is 120, the corresponding IZ is equal to 9 milliampere. That's it. So very, very simple question it is. Right. Right. In the next section, we will see how the range of input, what might be input minimum, input maximum, so that the Zener diode operates perfectly with breakdown region. We need to see. Again, range of RL, as I told, range of series resistance. If all the three are varying together continuously, how the circuit is maintaining constant voltage with variable currents. All those things we need to discuss.